atoms link up to form molecules, it typically involves an atom of one molecule, which we call the nucleophile, attacking an electrophile of another molecule. So the nucleophile is something that has extra electrons and it wants to share these. And the electrophile is something that's looking for electrons. So match made in heaven, right? Well, what happens next is that you form a new bond. But then what happens? So if you have formed a new bond and there's still binding opportunities offered up by that molecule that you bound to, so there's still binding opportunities offered by that electrophile, well, now you can keep building on. So do this enough and enough, and so hopefully I'll end up with a dinosaur skeleton, right? But what if you were to attack a proton, so just an H+? Well, this still would fulfill your desire for finding an electrophile because the electrophile, so this proton's looking for electrons, and so you could attack this, but now what happens? Now you have a dead end. So when you act, we call this acting as a base when we steal a proton. And so basically in either case, you have a nucleophile that is going to like attack something. If you attack like another molecule that still has stuff to offer, then we typically call that as acting like a nucleophile. Whereas if you attack like a hydrogen, we call this as like acting as a base. And when you do this, we have like a dead end. So it's not as clear here because the Lego still has a bump. But if you imagine that this Lego doesn't have a bump, now you have a dead end because you can't add anything else onto the end of a hydrogen because a hydrogen can only form one bond. That also means that if you have a nucleophile that is going to go attack and steal a proton, it's going to have to take that from the other molecule if it's not just like a free-floating proton, which free-floating protons don't really exist. They're typically like attached to water or whatever. So it's going to take that. And then what can happen is you can have things like elimination reactions where you can form double bonds and stuff. So there's all sorts of stuff that can happen. But we typically, these terms can get kind of confusing. So let's talk about nucleophile versus electrophile and a nucleophile versus a base. And so a base is just a specific subset instance of acting as a nucleophile where what you're stealing, what you're attacking is a proton and you're taking that proton and that proton has to be taken. You can't build on. So when you attack, you can think of stealing bases because you have to steal a proton if you act as a base. But if you act as a nucleophile, now you can build something new because when you add on to something, then you can keep adding on and keep adding on rather than forming this dead end. So these terms can get kind of confusing, especially because some things are good nucleophiles, but bad bases. And it also has to do with the effects that these terms, nucleophilicity and basicity, the actual specific measurements, they are different in how they're actually measured. So as we'll talk about, the basicity is a thermodynamic property. So like, where's your happy place at equilibrium? And nucleophilicity is a kinetic property. So speed, how fast does this attack and form this bond? And I'll show you some examples and how this comes into play in biochemistry, especially protein biochemistry, and how different side chains of amino acids, so protein letters, so some of them can act as strong nucleophiles and some of them can act as bases, but not nucleophiles, and it's this whole thing. So let's go and take a look. Okay, so today's post is going to be like a little more technical, so I'm not going to go deep into the background, but you can find a lot of that in past videos and posts, and hopefully that can help you if you want to follow along here. But basically, you need to know, so molecules are made up of atoms, and so like individual carbons, hydrogens, nitrogens, etc. And these are made up of smaller parts, subatomic particles. So we have the positively charged protons, which hang out in a central nucleus, kind of glued together by these neutral neutrons. And then you have this cloud of electrons whizzing around them. So the number of protons is fixed for an element. So an element is always going to have a certain number of protons. So and this is like their atomic number. So a carbon is always going to have 6, nitrogen is always going to have 7, oxygen is always going to have 8. But the number of electrons can vary. And so for reasons outside of the scope of this, atoms typically want to have this full like valence shell. So valence electrons are like the ones that are farthest from the nucleus. So the nucleus, remember, is where the protons are. So that's where the positive pole is coming from. That's helping rein in these negatively charged electrons. So the protons are staying put, but the electrons, you can like have atoms can swap and share electrons. And so when they share pairs of electrons, we form a covalent bond. So you can think of their electron clouds as kind of like merging. Part of their electron clouds merge, and you have this covalent bond. Some molecules are more like electronegative, so they're more like hogging when you have that shared bond. So like oxygen is really electronegative, so it's going to like hog these shared electrons. But basically that's another important point, is that these electrons are whizzing all around, and so we can only like say where they're more likely to hang out. But we can't like predict their precise location. And so if something's like more electronegative, then the electrons are just going to be hanging out near that atom more. But so you can see that because they're trying to get this full outer shell, and for most of the elements that we're talking about in like biochemistry and organic chemistry, this involves having a octet, so having 8 valence electrons. And so for like carbon, in order to get that, it can form 4 bonds, and oxygen can form 2, nitrogen can form 3, et cetera, et cetera. But if you look at hydrogen, it just has 1. So hydrogen, if it were to bond to something to form a pair, now it's like a dead end. And so this comes into play when we're talking about basicity. But so we've been talking about bases. Typically, we're referring to them in like their Bronsted-Lowry definition, where a base is something that accepts a proton. And so don't get confused, because we're just talking about protons, and you might be wondering, okay, well, wait, what is the difference? Like, how can we say like a proton is like those positively charged things we're talking about, right? Well, it turns out that hydrogen, it doesn't have any neutrons in its typical like most common form, and it only has a single electron. So if it loses that electron, now it's a proton. And so that's why we can say proton and like H plus interchangeably. And these really are the same protons that we were talking about before. It's just that just is what, because hydrogen only had that 1 electron, and you take that away, now it's just a proton. So that's where the basicity comes in to play. But basicity is really just a special case of acting like a nucleophile. So a nucleophile, so if we talk about atoms like sharing pairs of electrons to form a bond, well, like basically kind of like one thing has to do like initiate the relationship or whatever. And the initiator is going to be your nucleophile, which is the thing that is going to seek out a nucleus to share. So they want to get that full outer shell, but they also have specific like desires and wants and stuff. But so if sometimes, for example, something acts as, so it gets that full outer shell, but that leaves it with a charge imbalance. So this often comes into play when we have like a hydroxyl, an OH group gets deprotonated. And so when this happens, you have oxygen is going to have it's going to have a full octet. So remember, each single bond represents 2 electrons. So if you were to count along oxygen, you'd have 3 lone pairs, so 6, and then 2 from this shared pair. So it has its full octet, but it also has a negative charge. And molecules like, so remember we talked about oxygen as being very electronegative. So it likes having electrons, but it doesn't like having that charge. Molecules don't really like having a charge, especially a very concentrated charge. And so it has this negative charge, and it has a lone pair. Now it's a strong nucleophile, which is something that has an extra electrons or extra share of electron density. Because remember, we talked about how those electron clouds, like the electrons could kind of hang out more in one place or the other. So it can be negatively charged, and they're often stronger ones are negatively charged because they don't like charge, remember? And so when we're talking about like strength of something, like it's like, how is it going to react? So if something's unhappy, it's more likely to react, right? So having charge will make you more unhappy and more likely to react in the absence of like any other thing, just two, all else being equal, basically. So another place that you'll find a strong nucleophile is like in histidine. So one of the amino acids we'll talk about in the side chain. You can also find them in like double and triple bonds, where you have all of these electrons. You kind of have like this concentration of electrons and stuff. And these can form as like in these pi bonds. So basically sigma bonds are kind of like with the normal bonds that we talk about, like these single bonds, so sigma bonds. And then there's like pi bonds, which are form like different electron orbitals we don't need to go into. But that's where those pi bonds can form as sources of nucleophile sources. But of course, if you make a bond if you make a new bond, you have to then like break the bond, but you would still have like a single bond or a double bond. And so, yeah. Okay, so the nucleophiles now, so they have more electrons than, well, they have more like electrons than they could comfortably handle, because remember this, the number of protons is set. Oxygen is always going to have 8 protons. That's what defines oxygen, is an atom with 8 protons. But so protons and electrons are opposite, even equally but oppositely charged. So if your number of protons equals your number of electrons, that's the neutral form. What happens when oxygen gets to that octet? So if it gets that octet by sharing with someone, then it's only like responsible or whatever for 1 electron in the bond. So it would be, if it formed this bond, we could say that's not going to affect the balance of protons and electrons. But if it gains an electron, like just owns it for itself as a lone pair, like it does here, now the oxygen has an imbalance of protons and electrons because it's not sharing that electron with another atom like it is in a bond. And so for this reason, now you have this imbalance of protons and electrons, and you have this negative charge, which we said that things don't like. And so basically, if you have something that has more electrons or electron density than they want, then they're going to seek out someone to share that with. Because remember, you can like share the electrons and still gonna have like electrons from the shared pair to fulfill that octet without having to take on the burden alone of having like a charge or just having more electrons than the protons can comfortably deal with. And so where will they find that? They can find that in an electrophile, which is something that wants more electrons. So these are things with like too few electrons or electron density. So sometimes, but not always, fully positive or cationic. And they can be like things attached to electronegative things. So like the phosphate, the P and the phosphates in DNA. And so this can be kind of confusing if you look from the outside, you see these phosphates. These are like negatively charged, but the negative charge is on the oxygen. The oxygen is so electronegative. It's like pulling all of the electrons away from the phosphorus. Well, I mean, that's not why it's negatively charged. It has a full negative charge because it is like a full imbalance of protons and electrons. But the oxygens are pulling this charge, like all the electrons from those phosphorus oxygen bonds. The oxygen's hogging those electrons, and so this is going to make the phosphorus partly positive and electrophilic. Because it wants electrons, because the oxygen's stealing all its electrons. So when you have a nucleophile and an electrophile, they react and you form a bond. And so, so when something acts as, when a nucleophile does this though, what happens depends in what we call it, like classify it or whatever, depends on like what it's attacking. And so as we talked about before, a proton, it only has, I mean, like it fulfills that desire for a nucleus because it basically just is a nucleus. Like it just has that one proton. So if it fulfills the desires to have someone to share that electron with, but it doesn't get you anywhere in terms of actually building anything. So you can think of stealing bases. So something we call it acting as a base, because remember we talked about before how the Bronsted-Lowry definition of a base was that you were stealing a proton. And so here you can see, and the Lewis definition of a base is basically all nucleophiles, but typically we refer to like acting as a base when we refer to it taking a proton specifically. But you can see here that when you're taking the proton, and now you are basically have a dead end. You can think of stealing bases, because when you take a proton, because the proton can only form one bond, if it was attached to something else, then that something else is left without it. So you have to actually take it. You can't just like latch on. If you were attached to, so if sometimes the atom that you take it from is like okay with it. So for example, when you deprotonate the alcohol group, you would leave with O-, so you have that because the oxygen can hold on to that extra electron, and you have this it can be like more stable and happy because the oxygen is electronegative. But what if you were to steal a proton from something that is not electronegative, something like a carbon? Well, in that case, then you have the carbon really doesn't want to have that negative charge. It can't handle it as well as oxygen can because it's not as electronegative. So what you can happen is you could get what we call an elimination reaction, where basically you have something that's a leaving group, and you have this kind of so these arrows represent the pushing of electrons and the movement of electrons. And so you can see that you take this hydrogen, you take this proton, and then you form a double bond and kick off a leaving group. So this is an elimination reaction you'll see sometimes in organic chemistry. So when something acts, this is both instances of like acting as a quote unquote base. If something acts as a quote unquote nucleophile, this can happen in a couple different ways. You get this substitution reaction. So you can have, if you have like the same sort of thing, but in this case, you're adding on rather than just taking and going, and you're not forming that like double bond. But there are like different ways to do it and stuff. So we can talk about like if a nucleophile attacks a carbon and kicks off a leaving group, then we get a substitution reaction. So we take in this and we kicked off one thing, and now we've made something new. And an elimination reaction, so there are a couple of things that can happen when you act as like a quote unquote base and steal a proton. One is that you steal something from something that basically has extra. So like a hydronium ion, so an H2O plus or an ammonium ion. So if it has extra, you can take this and then nothing else has to leave because it had extra, right? But if you add to something that doesn't have extra, that can't spare it easily, then you can get like rearrangements where you get this elimination, where you get a double bond forming because they're trying to spread out that charge basically that you get from losing that proton that they don't want. And so then you get an elimination reaction. But in any of these cases, you have something that's a nucleophile attacking something that's an electrophile. And you can remember like a nucleophile with like a little smiley face, an electrophile with a plus sign forming a birthday hat. It's also important to know that nucleophilicity is a kinetic property. So it's asking like, how quickly does a molecule get to its happy place? So if you were to mix a molecule, so this is going to be our nucleophile and an electrophile, how quickly will the nucleophile attack and they react? So it's a speed thing. Basicity is the thermodynamic property. So basically, how far is that happy place? So if you were to mix a molecule and a source of protons, what proportion will be protonated eventually? So by eventually, I mean like equilibrium. So if you were to mix them, if you were to mix the molecules, eventually they would reach their happy place where there would be some proportion of it would be protonated and some proportion of it would be deprotonated. And basicity is asking how far toward, like how much is protonated at that point. The more basic, the more will be protonated, because basicity is acting as is like stealing a proton. And so if you're a strong base, you're going to steal a proton, and then
you have this, like you have a stronger probability or of stealing a proton, and if you have a lot of copies, most of those copies are going to be protonated. But yeah, so also as we talked about, basicity typically deals specifically with proton taking, whereas nucleophilicity is more broad reaching as to what's being attacked and taken. But basicity, acting as a base is really just a special instance of acting as a nucleophile. But when we talk about the like nucleophilicity or basicity, in terms of like these specific measurements, there we have to think about the differences in kinetics and thermodynamics, because you're talking about speed with nucleophilicity and just like endpoint with basicity. You can do things that you can like slow down a reaction, make it less nucleophilic without making it less basic. And so this can help you control whether you want something to act as like a nucleophile or a base. So you can help determine like reaction outcomes and that sort of thing if you have competing reactions. So what makes something a good nucleophile? So one thing to keep into account that we've talked about already is electronegativity. So remember, that's where you have a shared bond. You have electrons shared to form a bond, but one of the things is better at stealing the electrons. If something is better at handling electrons, then it's not going to be as eager to attack to find someone to help share the electrons with. So the more electronegative or electron hogging something is, the less willing it is to share its electrons. And so nucleophilicity is going to decrease as electronegativity increases. So if we look at you see that like carbon is less electronegative than nitrogen, which is less electronegative than oxygen, which is less electronegative than fluorine. And if we look at the order of nucleophilicity, so now we have that CH3 minus, so is where you have a negative charge on a carbon. That's going to be highly nucleophilic because the carbon is not electronegative. It doesn't want those electrons. But then as you go, so in nitrogen, NH minus, now you're getting more, you're getting less nucleophilic because you're getting more electrophilic with it's attached to. And so like oxygen, and then the fluorine minus. Another thing to take into account is steric hindrance. So steric hindrance basically is like atoms being like, dude, that's my personal space. So two atoms can't occupy the same place at the same time. And so when you have something that is like bulky, it's going to make it harder to get to like the attack point or whatever. So the bulkier the nucleophile, so the bulkier the thing that's attacking, the harder it's going to be to get in to attack something. And so the weaker the nucleophile. So something can be a strong base, but it can still be kind of like a weak nucleophile. If it's all big and bulky, if you have this steric hindrance, that's making it hard for it to like attack. Like that, what's that? I don't even know what movie it's from, but like, I have a big head and tiny arms, that dinosaur. Yeah, so if you can't like get in to do what you need to do, it's going to be hard to do it. And so you're not going to be acted as a strong nucleophile. We also have to take into account effects of the solvent, so the thing that's like dissolved in. So polar protic solvents, so things like water and methanol, they can hydrogen bond with the nucleophile, which hides it, decreasing its nucleophilicity. And we'll see this with our amino acids. So if you have the smaller the nucleophile, the more this hides them. So this effect is going to be greater for the OH minus group than it is for the S minus, and this is going to explain why this will explain why cysteine is a stronger nucleophile than serine, even though serine is a stronger base, because the oxygen, it can't handle the like concentrated charge as well as the thiolate is. So basically this hydroxylate group is less stable than the styrolate group, because the styrolate, you have this bigger atom, you can better share the electron density around, and so it is less eager to get the hydrogen. Like, it still really wants that proton, but it's less like desperate for it than the hydroxylate group. So this will act as a stronger base, but this will act as a stronger nucleophile. If you have a polar aprotic solvent, so such as like acetone or dimethylformamide, here you don't have like the positive, like you don't have the proton part that can form the hydrogen bonding. So even if you have like an oxygen that can serve as an acceptor, you don't have a donor. And so what's going to happen is you're going to preferentially like solvate or like surround the cations, so surround the positive stuff, and leaving the nucleophiles like naked, which is going to influence and increase their nucleophilicity. Okay, so what else? So we've talked, so what about negativity? Okay, so nucleophiles don't have to be negative, but an anion is generally a better nucleophile than a neutral molecule. So remember, they want that extra electron because it fills their valence shell, but they don't want the charge that comes with it. And the more negative charge it has, the less happy it is. And the less happy it is, the more likely it is to react as a nucleophile to get what it wants. And so we can see that these negative form. So like this is why the like OH minus is more nucleophilic than H2O. So even though this oxygen can act as a nucleophile, it's much less ready to do, and it can get protonated, it can act as a base, it can get protonated at the H3O plus, but it's much less likely to do it than this OH minus group. And similarly for other things. But the more, so charge though isn't the only thing, because the more you charge, that charge is spread out, the more okay it is with it. So it's the charge density that we really care about. So nucleophilicity is going to increase as the negative charge density increases. So the more concentrated that charge is, the more it's going to be a nucleophile, the more it's going to be desperate to get some help to handle that concentrated charge. So things that spread out the charge are going to decrease the nucleophilicity. So how can you spread out this charge? Well, one way is having a bigger electron cloud in your nucleophile atom. And so this is why we have that sulfur versus oxygen thing, where the thiolate sulfur is a weaker base than the hydroxylate oxygen because it has this bigger electron cloud, and therefore it can better spread out that negative charge, making it less desperate to get the hydrogen, the proton. But remember, we have to be aware of solvent effects, because in protic solvents, including water, the smaller atoms like the oxygen are going to be more hidden, and therefore they're going to be less nucleophilic because they can't find the thing to attack, right? And so this is why this cysteine is going to be a stronger nucleophile, even though it's a weaker base. Okay, what about resonance effects? So resonance effects, so like carboxylate, so we talked about like carboxylic acid. So like carboxylic acid, so like a double bond to an oxygen, it's carbon double bonded to an oxygen next to an OH group. How, like, so that's part of like amino acids. But like in our bodies, it's like always negatively charged because it's super duper acidic. So it's gonna want to lose that proton. And so when it does this, it has a negative charge. So this is a carboxylate group. And you might be like, well, we just talked about how the negative charge, they don't have like having this, so this would be a really strong nucleophile and base, right? No, no, no. This is so happy because when it loses that, it has this thing called resonance. So basically it can share these electrons among all of these. So we can draw these resonance structures, but really like it's really just being shared among these. And that makes it so happy. So it's not going to be reactive, because remember, you react if you're unhappy because you want to get happy. But if you're already happy, you don't need to react. But if you have like an O trying to, like in single oxygen trying to handle a negative charge by itself. Now it's not happy. So this is going to be much more reactive. As protein biochemists, we have to think a lot about nucleophilicity and electrophilicity and all of this stuff, because you can find nucleophiles in amino acids, so protein letters, and some of them in particular are ones, so you want to look for something with a lone pair of electrons to share, especially in the deprotonated state, because remember, the electronegative atoms like electrons, but not concentrated charge. That charge makes them unhappy, so it makes them more eager to react to become happy, and they react as an electrophile. And yeah, and so we have these nucleophilic reactions happening there all the time, especially like in enzymes. So the active site of enzymes, so like protein reaction helper uppers, a lot of the way that they help is by like either acting as a quote unquote base and taking a proton, or by acting as like a nucleophile and like forming like a little, like often you can have like covalent intermediates where an enzyme will actually hook onto something. We also see a lot of nucleophiles come into play when we're modifying proteins. So if you add like methylation or something to a histone, that's through a lysine or a ubiquitination. That's because this lysine can act as a nucleophile to form a bond to those things. We also see like acid-base reaction catalysis where histidine is like giving and taking protons and that sort of thing. And so remember, so we talked about how cysteine is a stronger nucleophile but weaker base than serine. Threonine, so now we have steric effects coming into play with threonine because it's bulkier. This is actually like a secondary alcohol as opposed to a primary, because this carbon is attached to a single thing, like a single non-hydrogen, and here you're attached to like two non-hydrogens or like two other carbons, and so this is a secondary alcohol. But basically it's bulky, and that makes it harder for this to react as a nucleophile. And so note with the with these, there's stronger nucleophiles, much stronger nucleophiles in their deprotonated state, because they have that negative charge. With an amine group, however, with these amine groups, they need to be deprotonated. It's not just like they're stronger when they're deprotonated. If they are fully like protonated, then they're going to have no electrons to spare for these reactions to occur. And so this is why they react in their deprotonated state. So for histidine, it has a pKa of around like 6 something, I think. I don't know, but I don't quite remember. But it has significant amounts protonated and deprotonated at like physiological pH. So you have a lot. Histidine is often involved in like these give and takes of protons. With lysine, it's usually in its positively charged state, and so it actually has to like deprotonate in order to do this. So typically you have like amino acids helping like make it the region more basic or whatever, and helping get rid of that proton so that the lysine can then attack. But then you can form like shift bases and all this cool stuff that involves this lone pair acting like a nucleophile and attacking something, and then you can like get things linked on and stuff. So yeah, so it's important to be able to recognize when something's like a nucleophile, and you don't typically, like outside of, I don't know, you don't typically come into the term like having to determine whether something's like quote unquote a nucleophile or a base or whatever. I don't So hopefully that helped you understand things. And yeah, so some of this terminology is stuff that you don't really need to be too concerned about, but you should know the basic idea of nucleophiles and electrophiles, as well as like why something can be like a nucleophile and a base, and what basically how some of the terminology is kind of wishy-washy, but you're safer with saying nucleophile, because all bases are nucleophiles, but not all nucleophiles are quote unquote bases. Yeah.